Hi everyone. So this is page 46, I believe, in the Gary and Grisham, basically chapter 2. This is number 1. I'm going to be doing A, B, and F. The reason I'm only going to be doing A, B, and F is because if you can do A or B, you can do every one of them except F. F is a little bit trickier, and so I'm going to be spending a little bit more time on it. Also, due to me messing up a lot, this is my third time making the video, so I'll just kind of skim you over the notes instead of writing out for you. Calculate the pH of the following, and that is 5 times 10 to the negative fourth HCl. The next one is 7 times 10 to the negative fifth NaOH, and number F is 6 times 10 to the negative ninth HCl. Okay, so basically what we're going to do here is this is just kind of where I wrote everything out. Now what I've done here is whenever I see a salt or something like that, I'm dealing with pH, I just cross them out because they don't play much of a part. So anytime I see potassium, chloride, iodine, fluorine, sodium, any of those that's going to make us a strong acid or a strong base, I just go ahead and cross them out. You can find those on either side of the periodic table. Usually they come in columns. There's some other exceptions and stuff like that. Probably a good idea to know all the exceptions. So the first one is pretty easy. You take this concentration. Because this is a strong acid, this is going to dissociate 100%. And when this dissociates, you're left with that. And so for every one molecule of this, you get one molecule of this and one molecule of this. So if this dissociates 100%, it goes all the way to the right, and this initial concentration was 5 times 10 to the negative fourth, then that means that this is going to be 5 times 10 to the negative fourth, and this will be 5 times 10 to the negative fourth. But this is really all we're measuring. So all we're going to do is we're going to take our H plus concentration, and we're going to take the negative log of it. And that gives us our pH of 3.3. The next one's a little bit different. It's basically the same concept as far as when it dissociates. You're going to get 7 times 10 to the negative fifth concentration of sodium and 7 times 10 to the negative fifth concentration of OH. What that means is that when you take the negative log of this, sorry, this is supposed to be negative log of this, you're going to get 4.15. But that is your OH concentration, so 4.15 is actually your POH. So to solve for a pH, we have to use this equation right here. Okay. And that should give you a pH 9.85. So those are kind of how you do those two. And everyone after that's pretty much similar. This is the only one that's really different. And how this is different is our H concentration that we're getting after this dissociates is really, really low. And water already contributes 1 times 10 to the negative 7th, 8th H. When water dissociates, it contributes, our H concentration from water is 1 times 10 to the negative 7th. And so what that's going to mean is that our water is actually in greater value. The amount of protons that are given to our solution is greater due to water. So we're going to have to add these two together. And we get this. When you take the negative log of this, you're actually left with 6.97. Okay. This is how you can kind kind of double check yourself for something that would be a silly mistake of just taking the negative log of 6 times 10 to the negative ninth. Right? So if you do that, you're going to find out that when you add acid, your pH will be higher than water because your pH of water is 7. So if you add more H plus to something that has a pH of 7 and your pH goes up, you know you did something wrong. And so try adding the concentration of water. See if how in any way you can get that pH down. And the reverse could be said for base. If you're adding OH and your OH concentration is less than water, which is 7 as well, then you know something's kind of funny. So the main point of this is that, or this also kind of helps out with an explanation I think that I gave that was a little fuzzy in a video that I pulled, which was the Siegel on page 92, number 24. The reason I pulled it was when I made an error, but also because people were getting really confused about when I was talking about the pKa being greater than 7. And this is kind of why. So in that problem, I changed the pKa to pKb, and I solved for the OH concentration. The reason for that is the pKa was 9.5. And when I did that, if you would have solved that equation, you would have had to include the water concentration. And I think you can solve it that way, but it's a lot easier to transfer that to the pKb once they give you a pKa that's greater than 7 for this exact reason. So if I really hope that that explanation helped people out. If it doesn't help you out at all, please forget it. And either come in and see me or Gassier, and maybe I could say it a different way. But I really hope that that does help some people out with why we do that. Okay. Well, again, I hope to see you guys at office hours, and please keep on commenting. I really appreciate everything people are saying, and I hope this helped out.